The 4262 oscilloscope is a dual channel high vertical accuracy measurement instrument. It has 16-bit digitizers which give a very high accuracy in the vertical plane, and this makes it very useful for audio measurements. But it still has a lot of general purpose diagnostic tools which again make it very useful for fault finding in audio systems. In this video we're going to look at an example of using the diagnostic tools and the measurement tools to find a fault on a stereo audio amplifier. The current display panel has 4 views, and these are selectable in the views menu, and we can select the number of viewports and then move the individual displays to the required viewport. So in the current layout we have the channel A and channel B of the stereo amplifier on the left hand side, and these are the time display modes, and on the right hand side again we have the channel A and channel B of the stereo amplifier, and this is the spectrum mode. So here we're looking at the amplitude against frequency of the signal. So this is in fact 1 kilohertz signal which is being generated in the internal generator. In fact it's generating a sine wave at 1 kilohertz. Other waveforms are available. And then the signal is being applied to the auxiliary input of channel A and B of the amplifier. The output is being developed across a 15 ohm load and then acquired with a ×10 probe. So on channel A here we have a ×10 probe. Other probe factors are available, and the vertical scale factor here now is 20 volts per division, and similarly on channel B we have a ×10 probe connected. So we can select each panel and then it is highlighted, and we can control each individual panel. So if we control the first panel here, we can then step through the memory and look at the individual cycles. Because the memory length selected is 100,000 samples, and this has been chosen to give enough resolution in the frequency domain to resolve each component of the input signal. If we require to look at the whole memory, we can close the zoom factor, and here now we see the whole 100,000 samples, or we can again zoom back in and increase the zoom factor and look at the individual sample. So here we have a zoom factor in fact of 512 on both channels. We're now going to increase the gain of the amplifier and drive the channel B in fact into a distortion. So I'm increasing the gain on the amplifier, and now we can see the power across the 15 ohm loads increasing, and eventually now we've driven the channel B into distortion. This is in fact a bias fault on the output amplifier of channel B. So here we can actually see it in the time domain that there is a problem, and obviously we can see it in the spectrum mode. Here on channel A the harmonics are down to -71 dBs, but on channel B they're only down at -23 dB, so we're getting a lot of measurement capability here to find that problem. There are more measurements available on each view, so if I again select the spectrum view, we could add a measurement to that view. So the signal is coming from source A, and if I wanted to measure, say, the amplitude at the peak, I could add that as a measurement. So here we see the measurement at peak is 18 dBs. If we want to remove the measurement, we can select the measurement and delete that measurement. So each individual view can be set up as required. I'm now going to decrease the gain slightly on the amplifier and take it out of the distortion area, so it's operating more in the linear area. So at this point the channel A and channel B look clean, but if we look in the spectrum mode, A is still very clean, it's -84 dBs down the harmonics, but in the B channel it's still only -58 dB, so we're starting to see some distortion already. So this instrument can very accurately measure audio signals and look for very low levels of distortion